Hi class, so this is the explanation video for this heating curve problem that we did in class today. Short answer number 6 here. How much energy is required to heat 156 grams of H2O solid at minus 17 degrees Celsius to H2O gas at 100 degrees Celsius? And I think the main problem that we're having with a question like this, with our heating curve questions, is really getting started. We can look at the information, we know some of the steps that we're supposed to do, but we don't know how to get started and how to look at the big picture for what's going on in a problem like this. So what you might consider doing is drawing a little cartoon. I know it seems silly, but sometimes this helps. So here I've got my block of ice. We're going to say that that's 156 grams of ice. And then we're going to heat it up, right? We're going to build our campfire and we're going to apply heat to that block of ice. And now I want to think, what is going to happen to that block of ice? And we're going to draw this diagram with this as our start point. And then we're going to apply energy, right? So as we apply energy, what's going to happen to this block of ice? So I think we all know, right? It's going to melt. And eventually, if we keep heating it, it will turn into all liquid water, and then that liquid water will evaporate. We'll boil it off, basically. But we need to sort of map out exactly what's going to happen. What are the processes that need to occur to go from this, 156 grams of ice at a certain temperature into my, gas at 100 degrees Celsius. So the information that we'll need to know that the melting point equals 0 degrees Celsius, right? So the melting point of 0 degrees Celsius, that's the temperature that the ice has to be at so that it will start to melt. So if we're at minus 17 degrees Celsius, the first step, we're going to have to heat our ice up from minus 17 to 0 degrees Celsius. So that's going to be step 1. At 0 degrees Celsius, now we can do our phase transition. We can go from this point here would be 0 degrees Celsius ice. This point here would be 0 degrees Celsius water, right? So solid to liquid phase transition. Then we're going to continue heating this up. So at this point here, we've got all water at 0 degrees, and we need to heat that up to the boiling point of water, right? So that's going to be 100 degrees Celsius. And at this point, we're going to have only water at 100 degrees Celsius, and then we can start doing our phase transition. So again, here, along this pathway, we're going to be going from 100 degrees Celsius water to 100 degrees Celsius gas. So this is going to be my end point. So drawing this diagram and really understanding what each of these steps represents and being able to say, at this point, this is what I have in my solution. At this point, this is what I have in my solution or in my system. That's really the key to getting started with this. Once we have this picture, then we can go through and fill in, the data. What's the energy that this takes? What's the energy that this step takes? To figure out the total energy, but this is really the starting point. If you do not start with the correct picture here, you're screwed basically. You're not going to be able to solve this problem. All right, so on this sheet, I've went ahead and redrew my diagram so it's a little bit easier for us to see. And I've got all of my other useful information here for the problem. And at this point in time, I'm just going to calculate all of these energies because the total energy required is going to equal step 1 plus the energy for step 2 plus the energy for step 3 plus the energy for step 4, right? So I just need to calculate all of those individual energies, add them all together. That's the way I'm going to do this. So step 1, we're heating the ice from minus 17 degrees Celsius to 0 degrees Celsius, right, to get to that melting point of ice so that we can do the phase transition. This is going to be a Q equals S times M times delta T type problem. And I'm going to use the specific heat of ice of 2.09 joules over grams times degrees Celsius as my S value. So 2.09. The mass that's given in the problem is 156. So that's grams, and I'm checking my units here. Grams, so those will cancel. And then my delta T, my change in temperature. So that's going to be 17 to go from minus 17 degrees to 0 degrees. The energy associated with this transition or this heating is 5,543 joules. So I really want to make sure that I'm paying attention to my units, or 5.54 kilojoules. So that's going to be the energy required for step 1. Step 2, that's going to be my phase transition. I'm going to go from H2O solid into H2O liquid, and there's a delta H associated with that. That delta H is this delta H of fusion, 6.01 kilojoules per mole. So that tells me if I want to turn 1 mole of H2O solid into 1 mole of H2O liquid, right, 1 mole of H2O solid into 1 mole of H2O liquid, then I need to apply this amount of energy per mole. Now, in this problem, I do not have exactly 1 mole. I need to calculate my number of moles, which ends up being 8.67. So 8.67 moles of H2O solid, multiply that by 6.01 kilojoules per mole, and that tells me that it's going to take 52.1 kilojoules of energy to do this phase transition, to go from 8.67 moles of water that's solid to 8.67 moles of water that's liquid at 0 degrees Celsius. It's going to take 52.1 kilojoules of energy. Continuing this problem, number 3, again we're back to Q equals S times M times delta T. This is going to be my heating up of the water from 0 degrees up to 100 degrees. So in this case, I'm going to use the S value for water, which is 4.18, so specific heat of water, 4.18, back to my mass of water of 156, and then I'm going to use 100 here because my delta T to go from 0 to 100 is 100 degrees. So now this energy is going to equal 65,200 joules, right? So 65.2 kilojoules. So this is the energy that will be required to heat up 156 grams of water from 0 degrees up to 100 degrees. The last step, step 4, is going to be my phase change. So here I'm going to go from H2O liquid into H2O gas. The delta H for that reaction is equal to 40.7 kilojoules per mole. And previously I found that it was 8.67 moles. Multiply that by 40.7 kilojoules per mole. And that gives me the energy required for this last step, which ends up being 353 kilojoules of energy. So that's a lot of energy to do this phase change from liquid water into gaseous water. So the last step is calculating my total energy. I'm simply just going to add all these values together, right? So here I've got 5.54 kilojoules for step 1, 52.1 kilojoules for step 2, so on and so forth for step 3 and step 4. So then my total energy, if I add all those up and round to 3 sig figs, is 476 kilojoules of energy. So that's the total energy that's required to do all 4 of these steps, right? So once we know what the steps are, it's not so bad, right? On the horizontals, we're going to be using our delta H information for fusion or for vaporization. As we're increasing the temperature, we're going to be using our heat capacities, using our S values for ice, using our S values for water. But coming up with this picture here, this is really the trick, right? We get so caught up in, oh, well, this is what the math is supposed to look like, but really drawing this picture here, that is really the most important part to solving a problem like this.